Very good. Okay, so the real gas, I'm going to talk about it. That's the last section of the chapter 1. And what do you know about real gas? And before I kind of write it down what's there. Do you guys anything know about real gas? I guess it's not ideal gas, right? What makes ideal?
Ideally.
Hmm?
It behaves ideally.
It behaves ideally, right? And what makes an ideal, and what is the assumption in the ideal? No interactions. And no volume or no size. That's the whole thing. So in a way, the ideal gas is like a point mass object that do not interact. And that's something that point mass object means has no size. And because there is no size, that's a correction. But each molecule does have a size, and I did talk to you about the gas molecule do have a diameter in the range of 0.3 to 0.5 nanometer. That's small, but it does exist, and we have to account for that. And what's most important is what I call the interaction. We have to account for the interaction for the ideal gas, and that's actually the main portion of today's topic that I'm going to talk to you. What kind of interaction are we talking about? If this molecule, there are two types of interactions. One is attractive interaction. The other one is repulsive interaction, right? So those are the ones that we want to. And what else do you guys heard about real gas? Did Dr. Matt cover the van der Waals gas? Have you guys heard about it? Not yet? No? I'm going to go through this a lot for this. And there are other ones as well. Okay? There are other ones. And probably you also need to know, like, what can I do? I mean, I'm studying this. Let's say I have this system in these small volumes, and when you compress it, the volume changing it, and when you heat it up, the volume changing it. So you guys can measure. I mean, this is also you have to really understand. As a human being, what we can measure? Can we measure pressure, volume, temperature? Probably this is it. This is something that we can measure mass and other things. As far as the property of the gas is concerned, pressure and the volume and temperature we can all measure, right? Can I use actually this concept to describe the interaction? And this is actually not a rocket science to figure this one out. I mean, even going to the van der Waals equation, there's something that I would like to even make an interest to you. There's one little problem of volume. Volume depends on the number of moles of the gas. So I'm going to put a molar volume, and it is an intrinsic property, not an extensive, not an extensive property. And do you remember that there is only two variables are independent? Right? Only two are independent. The third one has to be bound to be the same. But I'm not saying that I cannot change three independently. I'm just saying that this is a one that can be measured, and once your pressure is defined, volume is defined, you are doomed to have a certain temperature. You measure the temperature, you measure the pressure, your molar volume is doomed to happen for each real gases. Right? But here's a concept. If I let's say I have a system, and then I'm going to measure the volume. Okay? I'm going to measure the volume. And then I'm going to put this notation about now. This is a volume supposed to be. Using ideal gas. So well, I'm assuming this. So this is not an actual real volume. I'm using the equation of state. Then what is your ideal gas, the volume prediction? RT divided by pressure, right? So what you do, think about it. You guys can do this. I can measure temperature, I can measure pressure. And then I can predict it, the volume is supposed to happen as an ideal gas. And think about it, if this one is like that, and I'm going to, I mean, it's not a huge difference, but let's say this, the measured volume, this is a measured volume. So all the yellow circle is I have to make the measurement. I have to make 3 measurements, which is I can do. And if this is a case, what do you think? What kind of interaction do they think that they have? If there's no interaction, that's the volume they're supposed to have. And gas molecules collide each other to experience the interactions. But actually, your measured volume is bigger. Some cases, your measured volume can be smaller, right? What do you think about it? This has actually no interactions, right? One has a repulsive interaction, the other has a attractive interactions. Which one do you think the attractive interaction? Think about yourself as gas molecule. You have an attractive interaction. You have a more bring closer together, right? So this is an attractive interaction, right? Okay. And this will be a repulsive. And the people actually develop this idea about Z, which is a compressibility. This is another Z. This is more common Z, compressibility, which is a very simple idea, but they say the definition, conceptual definition is you measure your volume, is supposed to be, and I can easily say, oh, when Z is bigger than 1, when Z is less than 1, it has a repulsive, attractive interactions. So this idea makes sense. Yeah.
Does that mean when it's exactly 1, it is ideal?
Exactly 1 is an ideal. That's right. When you have when your Vn is same as Vm naught, that is an ideal, right? All right. I mean that should be that's the case because that makes an ideal, and your volume is then apparently volumized is an ideal. So people love to draw this diagram. This is the pressure. This is your Z value, which is Vm over Vm naught. And your actual reference point is actually 1, not 0. And let's say this is a 0 pressure. Okay? So this is something that anyone who can measure pressure, volume, temperature at the same time, they can start to put that in. And so let's look at this problem here. In the limit of pressure goes to 0. Pressure goes to 0. What do you think about Z? This is a one state. I want to go when you bring the pressure down and down and down. Your mean pre-pass getting longer and longer. And eventually this gas molecule, one is here, the other one is in New York City, right? Do you think that they have interactions? No. So if you go down to the 0, 0 pressure, always you will get here. That's a guarantee, right? No matter how attractive they are, if you separate them millions apart, and they don't have one, right? And then if you bring the gas molecule together, they can have an experience certain attractive interactions And eventually it can go this way. And this is very typical. Okay, and so this in the limit of that, that is a 1, and that's an ideal gas, right? Behave like an ideal gas. And this is a real gas, and people can do this all kinds of experiments. So when you bring the molecule together, they can have an experience interaction. But think about, we talked about the temperature, right? Temperature is a kinetic energy of the gas. If you bring the temperature go up and up, they move really fast. If they are moving fast, they don't have enough time to, I guess, hold them together and experience attractive interaction. In some cases, actually, let me see this. It's like this, and then they just go. Sometimes they do this. They don't experience any attractive forces at all, and this is a high temperature. This is a low temperature, and this is a, this is a high temperature. And there is a magic temperature where above which you can only have a repulsive interaction, and this is what we call T. This is called the Boyle temperature. Okay? So the Boyle temperature is actually a very kind of simple-minded, phenomenological way. Okay, that people do a bunch of experiments controlling the temperatures and to measure the volume, measure the pressures, and they tabulated some cases, which is this is a temperature smaller than Boyle temperature. They can have attractive interaction. Eventually, if the pressure goes up and up, they will see repulsive. I mean, you're doomed to happen. Okay? If you bring the molecule together and together, probably at this distance they have attractive interaction. What about this? And I cannot squeeze these two molecules together in the same place, right? So eventually everything is going to have a repulsive interaction. But there is a certain pressure level where this region is where your Z is smaller than 1. The volume is smaller than it's supposed to be. The gas molecules bring themselves together to have a smaller volume than is supposed to happen. Right? So that's what the concept of this. This is a very simple idea. And so this is a Boyle temperature. And have you heard about so now I'm going to bring the concept about critical temperature. Critical temperature. We call the critical temperature, and critical temperature we call Tc. And this is something that a little bit different concept than the Boyle temperature. And the critical temperature is actually more important than the Boyle temperature. And critical temperature is repeated a lot of times in here. Okay, so that's sort of the overview on the real gas, and then I'm going to start the next one.